Hi, my name is Jiaxiang Peter Zhu, and I am one of the maintainers of the opensearch-build repository within opensearch-project on GitHub. Today, I'm going to help you understand the initial setup of your local development environment, the structure of the repository, running some of the workflows in order to generate artifacts for opensearch-project, as well as achieve the solution of a first good issues as an example. Let's start by understanding what's the purpose of the opensearch-build repo. For simplicity, I'll refer to this repo as simply the build repo in the future. The build repo, as the name suggests, is used by the OpenSearch team to build OpenSearch and OpenSearch dashboards product artifacts. If you navigate to opensearch.org in your browser and click Download OpenSearch button, you'll see multiple different artifacts across different platforms and different distribution packages for both OpenSearch and OpenSearch dashboards. And those are the exact artifacts being built by utilizing the build repo codebase. You can run the codebase on your local development environment, or like our production system, running on an automation tool such as Jenkins. Our production Jenkins is open to the public, and everyone can access through their browser on build.ci.opensearch.org. You can check the workflows, read the logs, and even click the links within the logs to download a staging artifact that we just built on the pipeline. You can see the exact code in the build repo running on Jenkins just like you are running them in your local environment. There are more things to discuss and talk about on Jenkins and its related libraries, so I'll put that into another video. For now, let's switch back to the build repository and talk about its structures. The build repo has many different folders and files. The most important one is the source folder, which consists majority of the code in Python we're going to talk about today. If we go into the directory, we'll see multiple different workflows. The one we are focusing in this video is the build workflow. Upon checking the README file, it says the build workflow builds components declared in an input manifest from source, and that's exactly how it works. Go to this manifest folder in the root directory of the repo. You can see multiple different versions of manifest being put here. Let's use 2.4 as an example. In 2.4, we can ignore the test manifest for now because they are related to the test workflow. The build workflow is using the OpenSearch-240 YAML and the OpenSearch Dashboards 240 YAML for the corresponding product. These manifests are the aforementioned input manifests, not to be confused with the test manifest, as well as later on we'll have two more manifests called build manifest and bundle/dist manifest. Going to the manifest file, you can see multiple different components listed over here. Let's talk about this input manifest line by line. The first section, we have the build information, which is the product name OpenSearch and the version, which is 240. The second section, CI, we can ignore for now because it's mainly being used for Jenkins build. But later on, we're going to use this part for setting up the local development environment in Docker container. Third-part components, we're listing multiple different components in this exact order following their exact build or assemble dependencies. Each component can be a core engine code or a library or a plugin, and each of them corresponding to a specific repo. In this example, we have OpenSearch always on the first, because it is the core engine code we have to build before anything else. Follow-up is common utils. This is not a plugin, but a common library that multiple plugins use it to build their binaries. The third part is the job scheduler, which is a plugin of its own, but also a dependency of other plugins. The fourth one, ML Comments, is a typical plugin that requires some of the previous components being built beforehand in order to build itself. Rest of the sections are very similar following after. The most important thing here to understand is you have to have the name of the component, the repositories of the components, as well as the reference. Now this reference can be a tag, a branch, or a commit ID directly. We support all of them. Now that we understand the input manifest structure and content, let's actually check the command we need to use to run build workflow and build ourselves a small artifact to begin with. Scroll down in the build workflow README file and see the options available. Note it says build.sh options instead of build workflow options. That's because in the root directory, we have a shell script called build.sh. This shell script will serve as the entry point to trigger another script called run.sh, checking all of the dependencies we require before the runs. Then we'll run the source directory run-build.py for us in order to trigger the build workflow. A little bit complicated, so let's check the script one by one. In run.sh, we first check is there a workflow Python script right after. There is one, which is run-build.py, located exactly in the source directory. This will call the build workflow that we're going to run. We'll then check is there Python 3, pip, or pipenv installed, else exit. We'll then install all of the dependencies based on the pip file. After that, we're going to start the Python run by running the run_build.py script with all of the parameters we follow afterwards. And those parameters are the exact ones we defined in here. For the purpose of this video, we can ignore the -s snapshot, -d distribution, -p platform, -keep, -l log, and -v verbals. We will only focus on -a architecture and --component. -a is very easy to understand. It allows us to specify the exact architecture of the package we're building. For example, if you're on a x64 server of Linux, you are not specifying anything. It will only build a package that can be run on x64 CPU architecture. But if you want to cross-compile for an ARM64 architecture, you can manually specify -a ARM64 in order to build an ARM64 package. We do, however, suggesting users, if you want to build an ARM64 Linux package, build it on an ARM64 Linux system, because cross-compilation sometimes can cause issues. --component parameter allow us to specify specific component defined in the input manifest you want to build. If nothing is specified, all of the components within the input manifest will be built one by one. In our video, we're going to only use -s component space opensearch in order to save time. Now that we have a high-level understanding of the steps before actually running the build workflow Python code, let's go to a server, run the build command, and check the logs before we actually dive into the Python code. I have previously mentioned about the CI section within the OpenSearch 2.4.0 input manifest. Now we are going to copy the Docker image here and create a container out of it. We're going to start developing and building within this container because it has all the necessary dependencies. Let's first by putting the Docker image in your local environment. I assume you already have Docker installed in your local. So we're just going to pull the image. I already have the image in my local, so just trying to update, see if there's any discrepancies. If not, just start by creating a container in the background, and then we're going to give it a name called test opensearch container, and then give the image ID, and we started. Okay, yeah, I already have one running in the backend for the testing purposes, so we're going to use the one we just created. Let's log into it. Let's git clone the repo. cd into the repo. Before we do anything, let's check the Java home. So we have Java home pointed to JDK 19, and we have 17, 11, 19, 8 all installed over here. So the rule of thumb right now is that 2.x we're using JDK 17, but it's also compatible with 11, and 1.x also compatible with 11. So you can either switch to 11 or 17, but in our case, because we are doing 2.4.0 as an example, we're going to use OpenJDK 17 here. And if you want to know the JDK version, there are two ways. One is to go to the core engine, which is the OpenSearch, exactly opensearch.git repo, and check the repo version properties to see what's exactly the JDK version being used. Or you can just go to the input manifest. Remember, in the input manifest, we have the arguments of the image set to Java home equals to JDK 17. So you can just use that. So let's switch JDK to 17. So there are many ways to do it. I'm just gonna directly change in /c. So export Java home equals to Java 17 home export path equals to Java home /bin path. And then we can either relog in or we can just restart the shell. And then Java home should be this, which is 17. And then we'll check Java version. It's 17. And which Java is already in the right place. Now let's run the build command. So cd into opensearch-build, build sh, manifests, we're using 2.4, opensearch 2.4.0 .yaml, and then we have mentioned we're going to use -a x64 --component opensearch, and we're going to let it complete. As we can see, it first starts cloning the OpenSearch core repo based on the reference we mentioned in the input manifest. It now starts running a script called in the opensearch-build scripts component opensearch/build.sh. Now, not to be confused with the root directory build.sh, because there are two different scripts. We're going to talk about this later. Now it's basically running that build scripts, and whatever tasks that we assign to that build script will start running here. And want to mention one thing is that we previously entered -a to be x64, so this value has been successfully passed to the build sh, the second build sh, let's just call that to be easier, component build sh script. And the first task we're running, which is publish to Maven local over here, and we're waiting for it to complete. Okay, we're running the second task, publish Nebula publication to test repository. And we finished the Maven build, so we copy the Maven build to a certain location that we'll talk later. And here we are going to actually run the distribution archives Linux tarball ensemble. Because we didn't enter anything for the platform parameter as well as the distribution parameter, it will default to platform on the platform you are currently building on, which is Linux. And the default distribution will always be tarball. Okay, next we're compiling the core plugins, which is the plugins located within the plugins folder of the OpenSearch engine Git repo. All right, and then after everything is done, we're gonna record all of the zips, all of the artifacts we have built, and then put it into a manifest, as we mentioned before, called the build manifest. It's simply named manifest.yaml within the builds folder. So where are we now? Let's see what we have here. So we have one extra folders over here called tar. Now because we are building tarball tar distribution, it will create a tar folder. If you're creating zip for Windows, then it will show as zip. If you're creating RPM or deb, it will show as RPM or deb. So let's go into it. We only have a builds folder, and after you're running the next workflow, which is a Xamble workflow, it will show as a disk folder, but we're not going to talk about that. We're going to focus on build. So let's go into the builds folder. We're going to OpenSearch because we just only built OpenSearch. We didn't build OpenSearch dashboards. And then you can see that we have a manifest file. This manifest file is what we call the build manifest. It has all the information, all of the things we build, all the Maven artifacts, and then we have core plugins, which is the plugin I just mentioned. We have the tarball location. This is a min tarball. We call it min because it's for minimal. There's no plugins has been installed over here. After the Xamble workflow, if there's any plugin installed, or even though there's no plugin installed, it will become a bundle. And it will not call as min anymore. It will just simply call OpenSearch-240 blah, blah, blah. But for now, it's called min because it's only a minimal tarball, has no plugin on it. Guaranteed no plugin on it. And the location of this is just in the disk folder. And if you see the Maven folder, it basically has all of the Maven artifacts. And this Maven artifact also is in your Maven local, which is M2. So you're going to be able to see all of these exact same thing over here. It's just copied into this. And for the core plugins, which is the plugin located in the plugins folder of engine, core engine, OpenSearch, repository, you see all of the zips being added here. Now these zips are ready to install. If you're willing to try it out, you can absolutely just, let's say, extract these OpenSearch min tarball and then go to, for example, bin, right? And then you can just copy, let's say, one of the existing core plugins into it. So let's say we copy a discovery EC2 over here and just try it out. So let's say /OpenSearch plugin install, and we can do a file and do a pwd / give it the full path over here. You'll be able to install. Now I just click no here because we're not going to install over here, but you see the point. Let's get out and let's delete this folder we just extracted and go back to the root. One thing I did forget to mention is that you don't have to do what I did, which is directly logging into the Docker container and trying to develop here. You can, for example, if you're using VS Code or any other IDEs, you can just have a plugin or some sort or add-ons to directly connect into the Docker container and then start developing just like you're using a normal IDE. So we have a very good understandings, hopefully, from you on how the flow works. Just to do a review here, we first call the build.sh, the entry point script for build workflow. Build.sh will call run.sh. Run.sh will check if Python 3 installed, if pip or ppnv installed. If they all installed, they will run ppnv to install the corresponding dependencies in the pip file. After it's done, it's calling the entry point script for Python build workflow in runbuild.py. Runbuild.py has the following content. It will call things like, for example, build args, build recorders, build target, builders, or anything afterwards. What are these? Those are the libraries we have in the build workflow. Build args, very straightforward. It's exactly the arguments we read in that README file for things like log, snapshots, components, right? Architecture, all the things here. So basically, all the parameters you pass to the build.sh has been sent here. Now, build recorder is the one at the end of the run we just finished, doing all the recordings of all of those file locations and paths, and also create what? The build manifest, which is this manifest that we just checked. It has all the informations, locations of those files. It has the relative path of the min bundle, and if there is going to be another plugin, it will be afterwards over here. And then you have the information on the name, the version, the platform, architecture, distributions, all of these important informations, and for example, which commit ID that it builds. In this case, it will be the head commit of this ref, which is tags 2.4.0. Build target. Build target is basically telling you that, hey, I'm going to retrieve all the information from the input manifest, and then I'm going to create a build target. It will define what's exactly the version, and it will define what's the component version, because, for example, if OpenSearch is 2.4.0, then all of the component plugins is going to using OpenSearch 2.4.0.0. And then it's going to add the qualifier, add whether it's a snapshot or anything. Basically, all the build information related target will be created here. Next is builders.py. Builders is basically a class selector based on the type of input manifest. It will then decide which class to call for the next part of the build step. Now, if you want to take a deeper look, you can check these classes, but just so you know that because in the input manifest we're currently testing, we are including the Git URL as well as the Git reference. It will default to the input component from source classes being called, and then it's calling this builder from source py. Let's get back a little bit before we further dive into those builder code. This is the run build.py. We have talked about it. This is the one that actually calling all those classes from those libs. Now, this section should be very familiar because we just talked about it. So for each component within the manifest, right, it's actually trying to see what is the builder of it. We already know the builder is builder from source, not from dist, because we're giving the Git repo URL. So now you see it's trying to do the checkout of each component's repo. It will then try to do the build. After the build, it will then try to call the export artifacts into the build recorder. We have already talked about the build recorder. So let's see what's the exact code that we have in the builder from source that we'll talk about. This is the builder from source class, and we have seen the checkout function, the build function. The export artifacts function has been called by the run_builder.py. So checkout is straightforward. You can check the code if you want, but it's literally just git clone a repository, basically the component repository URL with the corresponding ref, and then put it into a working directory of a temporary folder that we're going to use later. As you can see over here, it's the exact same working directory. Now, the second part is build. In the build, we first need to find out what is the build script. We'll talk about this later. It's related to something called a script finder. After you find the script that is trying to run the build, it will then put the build script as part of a long build command. You see the build command also include all of these parameters we talked about, like -p, -a, -d, based on the architecture, distribution, or platform we've sent when we're running the first ./build.sh, right? If you don't enter anything, it will have a default value, like we talked about. Distribution will default to table, and architecture will just use whatever the server or the host or your local environment exact architecture to run, and platform will use that as well. So in our case, because we are running on a Docker image, which is CentOS 7, CentOS 7 is Linux, and we're running on x64 architecture, x86 64 if you prefer. In our case, it's x64 to be unified. It's building that, and the execution of that build script is running there. So which build script are we running here? If you remember, when we're trying to run the build, I have told you guys about a component build sh, or the second build sh that we have mentioned. Script finder find that build script and then run it. So let's see what's in the script finder. So in the script finder, let's find that function we're called, which is find build script, right? Find build script. In here, you see we have multiple different options in order to find that build script. So it can exist where? In the exact same build repo, in the component script folder, component name, build sh, which is exactly the ones we were using. So if you go back, you see the script folder. What's the component? Components. What's the name of the component? opensearch. And then what's the script? Build sh. We find that script. This is the script that actually runs when we are trying to build opensearch. There are other options as well. So for example, you see, we're going to have another build sh, but exists in the Git directory. So what is this Git directory? We have just checked out the source code of opensearch through opensearch repository's Git URL into a working directory. So that is it. The opensearch repos component name folder build sh, or the opensearch repos build sh in the root directory, or the opensearch repos script folder the build sh. But because we already found this file first, then we're not going to go down this list. We're going to directly pick this up. Unless this file has been deleted from the build repository, then it will try to find the second one, the third one, the fourth one, until it couldn't find anything. And of course, this one is another option as well. But you see the point. So let's see what's in this build.sh, the second build.sh, the component build script that actually build OpenSearch after checking out the code. So it's a shell script, and we have already mentioned these parameters, passing all of these values in, and we're seeing these tasks being run, right? Gradle task, publish to Maven local, publish Nebula publication to test repositories, and then copy the Maven artifacts into the output, which is our tar folder, Maven org, and then it will try to find the build target for the actual example of the tarball. So in our case, because it's Linux, it's tar is x64, it comes to here. The package is tar, extension is targz, type is archives, target, suffix, and get all these informations combined, put into one last Gradle command over here. Gradle w, distribution, type is archives over here, archives, target is linux-tar, we have already seen the logs, assemble, that's it, it's running this. And after it assemble a tarball, you'll be able to find that tarball. We see the tarball's name is opensearch-min. You will find that opensearch-min, and then we'll copy it into the output. We have mentioned it's tar, so it's tar slash builds slash opensearch slash dist slash opensearch-min opensearch-min dash 2.4.0 blah blah tarball full name. And then we'll build the core plugins. We have also seen build them and copy every single one of them into the core plugins folder, and that's where we see it. So if you go back here and go to tar, go to builds, go to OpenSearch, that's all I have. You go to dist, it copies to here. You go to Maven, it copies here. You go to core plugins, it copies here. So basically you see, when we run the script will build all the things we need. And then it will copy all of those artifacts into the tar folder. We point it as the output. And that's it. We have built everything, we copy everything to the tar folder, we get everything we want from the build workflow. So hopefully everyone has a good high-level understanding of how build workflow works and still remember some of the key points we're talking about. Let's try to use the limited knowledge we just learned to tackle an issue. So go to the Issues tab, find Good First Issue, and we're going to use this one as an example. So let's not read the description, just read the title. Source system os.py does not correctly return architecture for BSD platform. So architecture, we just talked about. How do we tell the build workflow what architecture to build for? There are two ways. Number one is we use the -a or -- architecture parameter, and we just simply pass x64 or ARM64 for it to build against. Now, that's one way. If we don't pass anything, then the default will grab from the system or the host or your local environment, directly grab from there, and then try to apply. But how does it work? How does our Python code know exactly what is your current system's architecture? Let's check out. We have previously mentioned there is a file called build-target.py, and build-target is the one that tries to sync user input and other default values into build-target and telling us whatever, like which version we're having, which architecture or distribution we're having, and this is exactly what we're looking for. So how do we know that this architecture? It's either coming from user input, which is x64, or if user doesn't input anything, it will coming from something called current architecture. So where is this function being called? It's from a system.os lib that we created. So let's go there. If we go to source system os.py, right? And we see the current architecture function just right here. The way it's grabbed the system's architecture is by using subprocess running uname-m. And then we're trying to find out what's your current running system's architecture. So in my case, I'm running x64 on a CentOS 7. It will be x86-64. And we'll convert it into x64 and return it, which is exactly the one that we can pass on -a or -- architecture parameter. If it's ARC64, if it's ARM64, we return ARM64. So that's not really a problem. Let's see what's on the issue saying that FreeBSD doesn't support this. So what exactly is the issue? Let's see. Apparently on FreeBSD, if you run uname-m, you'll return AMD64. And look at our code. We don't have that condition. We only have architecture equals to x86_64. We need a condition over here. So we can definitely just add a condition simply, but we also want to do some testing to make sure that it works. Let's switch back to the terminal and try to implement that. Let's quickly do a change over here. I'm gonna simply block this section and then just write architecture equals to AMD64. And let's see if this value arrow got triggered. So if we run build sh manifest 2.4.0 opensearch 2.4.0.yaml, we don't pass -a this time and let it get by itself. So component opensearch. That's it. And see if it runs. And it failed. That's exactly what we're expecting. Unsupported architecture, AMD64. So let's implement that part of the code by simply adding another condition. Architecture equals to AMD64. And try it again. Hey, now this time it starts running. And if we really want to know what's going on, we can just try to do a simple, well, if we really want to do that, we can definitely just do an echo, or a print over here. So just want to see exactly x64, right? We're going to this cycle. And exactly, we have this return x64, so we know it's in there. Good. So we know this code works. And let's restore this thing back. We now write a fix, but we don't really want to just push into a request, pull request or change request. We want to make sure the tests also include that, unit tests at least. Let's write the test cases. So the test cases exist in the test directory. And remember, we're doing something called system/os. So go to system and then go to OS. This is the exact file that contains the test cases. And this is the one that we care about. As you can see, initially, we're only marking uname-m to be x86-64 and returning x64, right? So in our case, we can add another AMD64 and see if it works. So let's test this by running pip-env run pytest and pointing to that test case, and it passed. So congratulations, we just made a very, very tiny fix in the build workflow. Well, technically not the build workflow in the system, but related to the build workflow part of it. And we write a small test case to test that condition we just add. Now it's time for us to commit this code and create a pull request. So previously, I directly copied the official repository's URL and then do a git checkout through HTTP. That's just for the demo purposes. For you to commit the code, the best practice is you click fork, and then you create a fork for yourself. Now, I already have a fork, so this is going to be my fork. And then I'm going to check using this SSH link instead of using HTTP. So I'm going to copy that. Now, one more thing, before you clone the repo, your own fork repo, with the SSH method, make sure you have run the SSH keygen -c and then your email address command. Make sure the email is the email you assign to your GitHub account. So something@something.com, and then it will generate a key pair for you. And then you can do the cat home.ssh idrsa.pub and then copy that public key and put it onto your GitHub account so that you can use this way to clone. So in my case, I already did it. So I'm gonna just clone this and then I'm gonna rename it to opensearch-build Peter Zhu Amazon because I already have another folder. I'm gonna accept this and I'm able to clone it, right? So now, in my case, I'm gonna go into here and see which file I have changed, right? There's only 2 files I have changed, so I'm just gonna copy those 2 in my fork. Now, in your case, you don't have to copy because you can directly develop in your fork repositories. Now, in the sense of the fork directory is not always synced with the upstream, which is this one. So what I'm gonna do is, I'm gonna come here and then grab that clone that I just done and then make a little bit adjustment. So I'm gonna delete this section. I'm gonna come here and then instead of my name and change this to opensearch-project, which is the official GitHub URL for the build repo, and then I'll just do git remote add upstream. So we add another upstream over here. We can git fetch upstream. Oh, git fetch upstream. Okay, we have fetched all the things in upstream. We'll do another one, git fetch origin, which we don't even need to do, but whatever. And now we can just try to see what is the branch here. Surely it's going to be in the main branch. Yep. So let's make sure our main is sync up with the upstream main. So let's do a git merge upstream main. Okay, now we indeed have a little bit difference between our main and upstream main. So good, let's push that into our origin, which is our fork. Now we can just do git checkout origin main. Let's say this is the fix system OS BSD. Now you can also put the issue number over here, just for easier recognition. Now we have this one. We're just going to copy those 2 files. Remember what files we're still having in here? Git status. Okay, so we're just going to copy this one and this one into opensearch-build my fork and well, actually, let's copy a little bit careful. Source system s.py, and then we're going to copy the other one, which is test. Yep. Now we're going to go back. Okay, let's add them. the status again. They're being modified. Good. Now let's commit them and add a good message saying add AMD64 as a condition for system OS.py to support FreeBSD architecture. FreeBSD x64 architecture. You can write more detailed commit messages. It doesn't matter. For my case, it's just for the demo purposes, but it's long enough. You can add more into the description as well. Just make sure it is very clear on what you're doing. Now, in my case, I forget to enter these, so I'm gonna add them. My email and my name. Okay, and make sure you don't have to add capital S because that's for the GPG key signing, but you have to have the lowercase -s, because if you don't have that, you are not signing the DCO. So you need to sign the DCO by adding -s. By doing that, if you do a git commit -- amend, you can see this is the one that the code is being signed off by me. And I can just push to my current branch, which is fix system OS BSD. So I'm going to push that. Cool. Now we can create a new PR and link to that specific issue. So we're here on the PR that we use the link provided to us to open it, but you can also just do it directly in GitHub. I'm just going to copy this title as the description. You can add more information if you want, or try to explain more, which is always better. For the issue resolved, if you think you can actually close this issue with this PR, you can just use the keyword closing. Now in my case, just to be a little bit careful, I'm just gonna only put the number here and without closing it. This is a bug, and this is a good first issue, and assignee is me. The reviewer will be any of the maintainers in the engineering effectiveness team, and that's pretty much it. But before we send it up, let's check the code. So we add an if condition over here, another condition, or architecture equals to AMD64. We add a test case which properly tests that. And see, we just discovered an issue that this shouldn't be called test x86-64. This should be called ARM64. So let me fix that. Sorry, AMD64. So I have just fixed the code, and the test now properly shows 11 passed instead of 10. That's great. But there's another thing that I forgot to mention, that if you go to .github workflow, and then you see the Python test, because all of these are the CIs we're going to run for your PR. You can already just pre-run these things like isort check and flake8 and mypy before all those are being run on Jenkins, so you can save some time and make sure that your syntax, your style, your dependencies are working fine. I'm just going to run all of them just in case. This one is a little bit slow. Okay, cool. There's no issues. So in that case, I'm just going to push again. Okay, it seems like I already pushed. Let's check the PR. We're back. Now the code is probably being named over here. Good. So let's create the pull request. And that's pretty much it. You have the pull request up. You have your change in the files. You're waiting for these checks to be completed. They're going to run all the Python checks, YAML lint, Groovy test. With this one is not related to the code we're changing because that's mainly on the Jenkins code. We're only doing the Python one, so we're expecting this one not having any issues, but the Python ones will be able to run because we have changed the Python code. But the thing is, all of these tests will be able to run no matter what. So if somebody can add some conditions on it to make sure that when only the Python code got changed, the Python test will run. Whenever the Groovy test got changed, a Groovy code got changed, Groovy test will run, will be great. But anyway, this is what we have right now. What you need to do right now is just to wait for all of the CI to complete. If the CI goes wrong, you can see the details in here. Just go into here and then check what exactly is the error and try to fix them. If there's nothing wrong, we can just wait for this thing to go to green and then wait for maintainers in the engineering effectiveness team to review your PR and see if there's any issues to give comments or approve it and merge. So with that being said, this concludes our video of explaining a little bit on what is opensearch-build repository and how does it works. We go into the details on some of its structures, the build workflow in particular, and how to set up the environment for your local development using Docker images, as well as trying to use the build commands to build a small piece of artifact which is very similar to what we are pushing onto the production opensearch.org website for users to consume. We then go into details on an issue that we tackle on how to make a fix to this issue and create a test case and eventually push the commit and create a pull request. So hopefully this can give you a kick start on what you can do to contribute to this opensearch-build repo. If you have any questions, feel free to open an issue and tag me or my team engineering effectiveness in order to explain and help you with your questions, and hopefully can help you contribute more and learn more about this repository and OpenSearch project as a whole. Thank you very much for watching this video and have a great journey in OpenSearch project. Thank you.